We now go to one of the most common applications of frequency response, which are filters. Specifically, we'll be discussing passive filters. So what is a filter? So it is a circuit designed to pass signals with desired frequencies while rejecting others that are undesired. For example, we have here a filter, and it has an input, it has an output. And let's say in the input, there are high frequency signals and low frequency signals. Okay. And let's say the output um, is a signal with a frequency that follows this one, the high frequency signal. That filter is called a high pass. Okay. This is a high pass filter, meaning it allows high frequency signals to pass. Effectively blocks low frequency signals like this one. Okay, there are generally two types of filters. We have the passive filter and the active filter. So a passive filter is a filter that does not contain any active sources, while an active filter, by the name itself, contains active elements such as transistors and op amps. Filters can be categorized in four classes. We have the low pass filter. Um, so there are filters that allows low frequency signals and blocks high frequency signals. High pass filter, it's the opposite of the low pass filter. It allows high frequencies but stops low frequencies. The bandpass filter, so this is a filter that allows a range of frequencies to pass while it blocks the frequencies outside those range of frequencies. The bandstop filter is the opposite of the bandpass, and it allows frequency outside a certain band while it blocks frequencies within the band of frequencies. We can characterize filters by their transfer functions. For example, for low-pass filters, um, the magnitude of the transfer function tends to go to unity for low frequencies, while it tends to become zero at high frequencies. So for a low-pass filter at low frequency, the output here is uh, almost the same as the input. Okay, while here for high frequency, the output, if it is a voltage, is zero. Okay, for high pass, for low frequencies, the magnitude of the transfer function is uh, is a zero. It tends to go to zero, while at high frequency it tends to go to unity. Now for a band pass, um, for low frequency, it has a zero magnitude of transfer function as well as for high frequency. While for a bandpass filter, the magnitude of the transfer function for low frequency and for high frequency are both unity. Now, there is another characteristic called the cutoff frequencies for low pass and high pass filter. Okay, so and for band pass and band stop, we have what we call the center frequency. Okay, so what are these characteristics? So first of all, what is a cutoff frequency? Well, a cutoff frequency is the frequency where below that or above that frequency, uh, the signal might be allowed or blocked depending on whether you're using a low pass or high pass filter. So for example, for a low pass filter, um, if you're above the cutoff frequency, that means the signal is considered blocked. For a high pass filter, that signal is considered um, allowed through the filter. Now for band pass and band stop filter, we have the center frequency for, so at the center of the band of frequencies for a band pass, the magnitude of the transfer function tends to become 1, while for a band stop, the magnitude of the transfer function tends to become 0. A low-pass filter can be formed using a series RC circuit where the output is taken across the capacitor. Um, this filter has a transfer function equals to this. So that transfer function has a simple pole at negative 1 over RC, so the magnitude of the transfer function. The magnitude for low frequency goes to unity, and this is also the maximum uh, magnitude of the transfer function. Um, and also the transfer function tends to become 0 at high frequency. So for very high frequency, the graph here tends to go to 0, while at low frequency, it tends to go up and goes to unity. At omega equals the cutoff frequency, so let's say this is the cutoff frequency there. The magnitude of the transfer function uh, equals this one, so it's 0.707, and it is also 0.707 of the maximum magnitude of the transfer function. Take note that for this filter, the cutoff frequency occurs at this frequency, 1 over RC. So we can say that we can manipulate the cutoff frequency by manipulating the values of R and C. So 1 over RC is called the cutoff frequency, and at that frequency, the magnitude of the transfer function is equals to this. It's 0.707 of the maximum magnitude of the transfer function. Likewise, for high pass filter, we can form that filter by using the same RC series RC circuit, but this time we take the output across the resistance. So the transfer function of that will be like this, So notice there is a constant gain which is equals to RC, a zero at the origin, this one, and a simple pole, so this one. Now the cutoff frequency for this is also 1 over RC. So again, so this is the plot of the transfer function. For low frequency, the magnitude tends to go to 0, and um, it goes to 1 for high frequencies. Take note that there is also a plot here for ideal plot of the transfer function, and it looks like this. So be so after the cutoff frequency, we it is a constant unity, and before that it is a 0. Okay, so the same for low pass filter. There's also a plot there for the ideal transfer function. So let's have an example. Uh, so here we are to design a low pass filter using an RL circuit. Okay, so we can make a low pass filter using a series RL where we are taking the output across the resistance. Now the problem states that the filter uses a 40 millihenry coil, and the cutoff frequency is given. It is equals to 5 kilohertz. So we're required to find the volume R for this filter given the cutoff frequency. Take note the cutoff frequency is given in kilohertz. In addition, we are required to sketch the magnitude and phase-mode plot of the transfer function. So if we're going to make a rough estimate of the transfer function, okay, so this is the omega sub omega. Um, so the plot would look something like this, okay, and maybe the cutoff frequency is somewhere here, okay. So this is the maximum magnitude of the transfer function, okay. This is also the maximum, okay. So this is also the uh, maximum, and here it could be a unity or even higher or lower than that. But the minimum would be a 0. Okay. So the maximum here is we're not yet sure if it is a unity uh, or not. Okay, but certainly it's not 0. Okay. Now take note that omega sub c is 2 pi times 5 kilohertz. Okay. Okay. So we compute for the transfer function first. So using a voltage divider uh, to get this ratio, we will arrive to this expression, and simplifying that, it will give us like that. So it is just a simple pole with P equals negative R over L. Okay. We extract the magnitude of this transfer function, so we write it this way. So the magnitude is this one, So if you take the magnitude of this, so take note this is a complex expression, and uh, and the magnitude for this would be square root of 1 plus uh, omega divided by r over l squared. Okay, so there's a square here, and we simplify this, we will arrive to this one, and simplifying further, we will get this one. We want to know the magnitude at very low frequency, so we let omega equal 0, and if we do that, we will get a 1. Okay, so the value of this is equals to 1 for omega equals 0, which is also our maximum magnitude. Okay, for high frequency, we let this omega equals infinity, and that should give us a 0. Take note that our objective is to determine what is R, and we are given the um, cutoff frequency as equals to this one, and we wanted to know what is the formula for the cutoff frequency in terms of the values of L and R, and we don't have that yet, and that is what we want to know. Okay, so from the uh, expression for the magnitude of the transfer function, if we let the frequency equals to the cutoff frequency, we know that the magnitude of the transfer function there is equals to 0.707 of the maximum magnitude. And since we already know the maximum magnitude, which is equals to 1, that means that this one, which is equals to this one, must be equals to this one. Okay, so from this equation now, we can compute for omega sub c. Okay, so that means that this must be equals to this one. So computing for omega sub c, so we can do that by squaring both sides. Okay, so we square this to eliminate the squared function, and that should give us this one. And this should be equals to 2 pi times 5000 hertz. So we can compute for uh, R there, and this will give us that value of R. So the value of R means that uh, with an inductance of 40 millihenries in series with this, we can produce a low-pass filter across the resistance with a cutoff frequency of 5 kilohertz. Now, we can uh, rewrite our uh, transfer function in terms of the cutoff frequency. So we know the cutoff frequency to be R over L. Okay. And we can replace this term here by omega sub c. So this one here is omega sub c, So we can replace this by this. However, this one is also 1 over, see, so this will cancel the 2 pi's, and that will give us this one. So therefore, the magnitude or the transfer function can also be expressed in terms of the cutoff frequencies. We can plot the Bode plot. So this is so what we have is a simple pole. So before 5 kilohertz, so let's plot this in terms of kilohertz. So before 5 kilohertz, that must be a flat line. And above, the Bode plot should slope downwards with a slope of minus 20 dB per decade. Okay. We can find the actual magnitude of the transfer function by substituting here 5 kilohertz, and that should give us uh, 3 dB or negative 3 dB magnitude. Let us have a second example. So here in the circuit, we are to obtain the transfer function V out over V in, uh, identify the type of filter that we have, and determine the uh, cutoff frequency or the corner frequency. So let us make R1 equals R2 equals 100 ohms, and L here is 2 millihenries. So this is actually the answer. Okay. So to solve the transfer function, we can use nodal analysis. So let's see, this is my ground here, and this is my node A here. I can perform a KCL on that node. So current entering equals current leaving. So this is current leaving, current leaving. Take note there that S equals J omega. We can transform that equation into this one. So from here we can get the ratio, and that should give us this ratio here, which when simplified will give us this compact answer. And returning back the value of S, this will be our final expression. So there it is again. Now we can get the magnitude. So this is the magnitude. So the magnitude of this at the numerator is simply this, while the magnitude of this uh, can be determined using the Pythagorean expression. So it will give us this, and simplifying. Okay, so we bring this omega L in the denominator. That will give us an expression that is like this. So to find out the type of filter that we have, we can let omega equal 0. Okay, if we let omega equal 0, that means uh, this term here will become infinite, and the whole expression for the transfer function will become 0. On the other hand, if we let this infinite, okay, uh, this becomes a 0. So therefore, this becomes r sub 2 divided by the square root of uh, r1 plus r2 squared. So the square there will disappear, be the squared sign, and that should give us this one. So since we have a 0 at low frequency and a non-zero result for high frequency, that means this is a high pass filter. Take note the magnitude at high frequency is not a unity. In fact, this is uh, less than 1. Okay. Now, so this is the expression again that we have for the transfer function. Now we want to know the cutoff frequency for this circuit. So to do that, we substitute omega sub c to this expression, and again we said that the um, the transfer function at the cutoff frequency must be equals to this times its maximum, and we know the maximum to be this. So we equate this with this one and then solve for omega sub c. Okay, so we can eliminate the squared sign by squaring this, and doing that will give us this expression, and in solving for omega sub c, that should give us this expression here. And substituting for the values of the resistances and L, you will get omega sub c equals to 25 kiloradians per second. So let's go back to our first expression for the transfer function. So this is our original expression. And let's do some manipulation. So let's say I'll group this and this one, I'm going to transfer this outside. So that means I will have this expression here. So take note that in this expression, this one is actually our omega sub c. Okay, so therefore I can uh, replace this expression. So take note that L here cancels. So that will give me this simple expression. And this one is zero 0.5. Okay, so 100 over 200 should give me 0.5. And I should arrive with this expression of the transfer function. Then I can draw the straight line Bode plot by first converting this into its standard form. So that will give me this one. And now I can plot this transfer function using the straight line Bode plot. Okay, so here's the transfer function again. So it has a a constant gain, uh, 0 at the origin, and a simple pole. Okay, so these are the constant gain, uh, 0 at the origin, and the simple pole. So combining those plots, that should give me this uh, straight line body plot. And take note that this is my corner frequency here, which really corresponds to our omega sub c. Okay,